So hello, everyone. We are pleased to have Professor Barna Saha with us here today from UC Berkeley, Department of Industrial Engineering and Operations Research. Professor Barna is a leading expert on algorithms complexity and large-scale data analytics, and she's actually going to give us a tutorial on a very interesting topic that perfectly complements the topic of the first tutorial that we heard earlier today, which was about higher complexity classes, Phi, MP, and fixed parameter tractability. Instead, Professor Barna now is going to tell us about fine grained complexity within the class P itself. So please, Barna, take it away.
Thank you, Mahmoud, for the introduction, and thanks to the organizers for inviting me for this tutorial. So let me try to share the screen. Do you see my screen, Mahmoud?
Yes.
Okay. So feel free to interrupt anytime you have questions. So today my talk is about approximation algorithms for large-scale data analysis, where my goal will be to give you some examples of problems and show you how approximation algorithms can be utilized to have a much better solution in terms of mostly in terms of time complexity, but in general, the goal will be to show the effectiveness of approximation algorithms when dealing with large scale data. Okay. So we are pretty familiar nowadays with the kind of statistics of large data that we see in various mediums, in various social mediums. Like these statistics could even be a little old, like now the numbers have even grown more. So it's saying that there are 2.7 zettabytes of data that exist in the digital universe. Again, this could be a few years old, where Facebook, it stores and analyzes 30 plus petabytes of generated data every day. Akamai, it analyzes 75 million of events per day. Wait a second, so I can see so many of you. Like, let me just, okay, that's good. Okay. Yeah, so Facebook, Akamai, they're analyzing this huge amount of data that for their everyday purpose. And according to the estimates, the volume of business data worldwide across all companies, it's doubling every 1.2 years. So these are, again, like some statistics which we now encounter at, like, whenever we have to deal with large scale of data, we are encountering this kind of mind-blogging statistics. And many of the data that's being generated from these different avenues, they have poor data quality. So dealing with large data, there are advantages, and like we are obviously getting access to so much information, but then there are a lot of challenges as well. So when we are designing algorithms, so my main research agenda is to design efficient algorithms. So as an algorithm designer, now we are faced with lots of challenges. Like the data that we just saw is like voluminous in nature, but it's also might have high velocity, like it's being updated very frequently. It's coming from many different sources. And there are obviously a lot of noise, a lot of data quality issues in this data. So as an algorithm designer, you have to be mindful about time complexity. Obviously, you want to design efficient, like very fast algorithms. Space complexity, you might not be able to hold the entire data in your main memory. Again, the data could be noisy. The data could be evolving over time. Therefore, you might have to design algorithms that can deal with this dynamic nature of the data. Sometimes you have like you have machine learning. Think about machine learning problems where it's very important to have efficient sample complexity. Like you want to minimize the amount of training data over which you have a huge amount, but you cannot really train on that entire data. So you have to select the data in an efficient way so that it gives you an accurate result, but it also it's an efficient process. And sometimes the algorithms needs to be distributed because of the voluminous amount of data. So all these different aspects adds to the complexity, adds to the challenges that you would face as an algorithm designer. So previously, like before all this data explosion happened, we would say any problem that runs in polynomial time to be efficient, whereas a problem is inefficient if it's like NP hard. But definitely this crude distinction of efficiency in terms of polynomial time versus NP hard is not justified when we have this large amount of data. And dealing with this kind of data, even if there is an algorithm that runs in, say, quadratic time in the size of the data, could already be infeasible. Okay. So in this region, we want to know whether it's possible. What is the true complexity of a particular problem? Is it like linear? Is it quadratic? Is it cubic? And so on. Because obviously our goal is not just to give a polynomial time algorithm. Our goal is to give something which is much more efficient. This is a quote from a monologue by Scott Aronson, where he said, yes, of course, that's the goal. We really want to understand what is the true complexity of a problem. We want to know whether it's linear, whether it's quadratic, whether it's cubic, something in between. But the unfortunate scenario is that we even do not know whether P equals NP or not. And if we do not understand that, how are we going to understand whether how are we going to classify problems into these finer grained classes like linear versus quadratic and so on? So that kind of questions is just out of reach of today's, given the current status of computational complexity. So that's something we have no handle on. So what can we do? So in order to overcome this challenge, what the researchers have done over the last many years now, like over the last decade or more than a decade, that they have come up with some more stronger conjectures, the conjectures which are much stronger than just saying P not equals NP. So instead of saying satisfiability is NP hard, now assume that satisfiability requires almost exponential 2 to the n times. So you have n variables and you want to solve CNF SAT, and assume that CNF SAT, it's just solving it requires as much time as it would require for an exhaustive search. That is, you will try all possible assignments of the n variables that will require you 2 to the n time. And suppose that is the best algorithm. There is nothing better than that. So that's roughly speaking, that is the strong exponential time hypothesis, which is a much stronger conjecture than just saying P not equals NP. So assume that conjecture, and assuming that, can you show this kind of finer grained classification of problems? So not just this strong exponential time hypothesis, there are various other hypotheses or other conjectures that you can rely on to develop this kind of classification of problems. One of them is the APSP hardness, which says, suppose you have a graph on n nodes, a dense graph, where you have about order of n square edges, and these are weighted. That suppose the graph is directed, and you want to find the shortest path among all possible nodes. So this all pair shortest path, even like people have tried to come up with faster algorithms for all pair shortest path, but like still now there is no algorithm significantly better than n cube that exists to compute all pair shortest path in weighted graphs, weighted dense graphs. So assume that APSP, this all pair shortest path, is cubic hard. Assuming that, can you say something interesting about the complexity of other important problems? There are another conjecture which is also very popular is three-sum hardness, based on which, like, people have tried to classify some problems which are quadratic, which could be quadratic hard and so on. So again, this is not an exhaustive list. There are many others, but these are just some of them which are very popular and based on which people have tried to classify problems. So before all these work on conditional hardness, so these are like, obviously these are much stronger conjectures. So before classifying the polynomial time problems based on these conjectures, this is how polynomial time problems used to look like. There are many important problems here. People have always tried to come up with faster algorithms for these problems, but there was no such understanding like how these problems are related, what could be the true complexity of these problems, what happens like if I improve one problem because we didn't know the connection, this had no implication for the other problems and so on. So we just didn't have a proper view of the polynomial time problems. But due to work by many researchers and basing the hardness on these popular conjectures, now the polynomial time problems look something like these, where we can classify problems like into different classes, and we know that if we improve, like for example in the first circle there are some of these problems. All these problems are, you can design easy algorithms which run in quadratic time. And now we know that all these problems are related to satisfiability, that if you can improve the quadratic running time for any of these problems, you will break the strong exponential time hypothesis, which is very surprising because all of these problems are just they have quadratic running time and satisfiability. We are just really talking about an NP-hard problem, that this connection between an NP-hard problem and low polynomial time problem was very surprising, that improving a low polynomial time complexity of a low polynomial time problem could directly lead to an improvement of getting a faster algorithm for satisfiability. Similarly, if you're looking at the second circle here, here are some problems which are known to be as hard as Boolean matrix multiplication. So all these problems, like if you can improve these problems running time, you will have a better running time for Boolean matrix multiplication. And in the third circle, the problems, these all have long-standing cubic algorithms that run in cubic time, and improving any one of them will break the APSP conjecture. Okay, so now due to all these works, now we have somehow been able to classify the problems in polynomial time into these well-separated boxes, so that we know that improvement in any one of them will lead to improvement of one of these conjectures. And sometimes there are also some equivalents, like for example, in the third box, all these problems are like, if you improve on, so these are just not one-way reductions. So these are both-way reductions. So let's look at some of the problems from these boxes. So let's look at this third box, and these problems are all based on all pair shortest path. So in all pair shortest path, again, as I mentioned, that you have a dense graph, you want to compute the and it's a weighted graph, you want to compute the shortest path among all these problems. So how do you solve this? Solve the all pair shortest path? Well, you can just write a dynamic programming where you are trying to compute the shortest path between I to j by looking at how I can move from I to k and then k to j. And we are taking minimum over this k. So, and if you look at these, this is basically a matrix multiplication over mean plus product. So the traditionally, the product is like the plus here, and the summation is now the minimum. So this is a mean plus product. So all pair shortest path computation is in fact equivalent to computing mean plus matrix product. So for matrix multiplication, for the normal matrix multiplication, we have a faster running time, right? It runs in much like n to the omega time. Omega is the exponent of fast matrix multiplication, which is about 2.37 something. But here, the mean plus product, since the mean plus is not a ring, it's a semi-ring. So for mean plus product, there is no algorithm that runs better than NQ. Like there is no algorithm that runs in n to the 2.99 time. And this mean plus matrix multiplication and all pair shortest path, these are equivalent. So if you can improve in mean plus product, you will immediately improve the all pair shortest path running time. So this entire, all these problems here, which is like computing negative triangles, finding replacement paths and betweenness centrality and so on. Like if you have an improvement in the mean plus product computation, you can improve the running time of all these problems. Okay, so all pair shortest path and mean plus product are basically equivalent. And this chart here shows like, so it's written as n cube, n cube, n cube, which doesn't make much sense, but what has happened here is like there has been some tiny improvements, like shaving off some log n factors in the running time. And the last one is basically, it's a work by Ryan Williams in 2014, where he was able to improve the running time more than polylog, but not by any polynomial factor. So it's not n to the 2.99, so it's not a truly subcubic algorithm, but the improvement is still better than polylog. Okay, so over all these years, so people have really tried to improve the complexity of all pair shortest path or mean plus semi-ring or matrix multiplication of mean plus product. And have failed to get a better than n cube running time, but it's really, nobody knows whether this should be the right answer or not, especially with Ryan's result, where he was able to improve by more than a polylog factor. There could be a possibility that sometime in the future, we will get a better than cubic running time for all pair shortest path. So a truly subcubic algorithm for mean plus product will be a major breakthrough, resulting in a huge number of graph and string problems, polynomial time problems to have a faster running time. So let's look at another problem from the first box, which is about string edit distance. And I'm just picking these problems because these are the problems I'm going to elaborate a little bit more as I go through my presentation. So string edit distance, this is a problem which was introduced in 1965 by Levenstein. And it's a basic measure of distance between strings. So we are given two strings and you want to know what is their distance, how similar they are. And string edit distance basically says like you compute the minimum number of insertions, deletions, and substitutions using which you can transform one string to another, and that's the string edit distance. So if we are looking at this example here, in this example, if you delete this T, if you substitute this A with a C, then it becomes ACC, so it matches here. And at the end, if you insert a T here, then there is this double T, it will match here. So with these three edits, one delete, one substitution, and one insertion, you can transform the string T to string S. So the edit distance between these two strings is just 3. And edit distance has applications in genomics, in text processing, in pattern matching, and so on. So what is known for string edit distance? Like the string edit distance, it's like if you can solve it you can solve string edit distance again using dynamic programming. And it's if you can in n squared time, where n is the string length, assume both the strings have length n. And if you can get an n to the 1.99 algorithm for string edit distance, that will refute the strong exponential time hypothesis. And here is the algorithm, like the dynamic programming algorithm. So what do you have? You have a quadratic table, you have an n squared table, and you want to compute the edit distance, like the box here, the ith row and the jth column of the box basically specifies what is the edit distance between the length I prefix of the first string and the length j prefix of the second string. Okay, so the ij box represents the edit distance between the prefix of length I in the first string and the prefix of length j in the second string. If you want to compute this, there are three ways that you can come to this box. Like either you can match, either you can delete the ith symbol of the first string, and then you compare the edit distance between the I-1 length prefix with the jth length prefix of the second string. So that's here, edit distance between I-1 and j. You have deleted the ith symbol from the first string. Or you delete the jth symbol from the second string, you pay 1 here, and you compare the edit distance between the prefix of length I in the first string and the prefix of length j-1 in the second string. Or what you do, you try to match between the ith symbol and the jth symbol of the first and the second string, and then look at the edit distance between the prefix of length I-1 and the prefix of length j-1 in the second string. And when you are trying to match the I symbol and the J symbol, if they match, you are not paying anything in the edit cost. But if they don't match, then you have to pay for substitution cost. So that is the cost here. Okay, so there are three terms to compare. So that takes constant amount of time. So therefore, filling up a particular entry here will require constant amount of time. And you have to fill up this entire quadratic table. So that requires n squared time. Okay. So that's why the time complexity is order n squared. If you're filling up this entire table, the space complexity will be order n squared. But as you see that when you're filling this row, you basically only need the information in the previous row, right? So that if you just keep that solution, you can improve the space complexity to linear. So time complexity order of n squared, space complexity to order of n. And the lower bound is showing that if you can beat this time complexity, that will refute the strong exponential time hypothesis. So that's your string edit distance. Let's look at one problem from this was the middle circle. So this problem is RNA folding. So what is RNA folding? It's a very basic problem in computational biology. So here so the version of RNA folding that I'm describing here is the very first model for RNA folding proposed by Lusinov and Jacobson in 1980. Since then, there had been more complex models for RNA folding has been proposed in the literature. But all of these kind of builds up on this very first model that was specified like 40 years back. So you have nucleotides in RNA, they form complementary base pairs. There are 4 different types of nucleotides, C, G, A, and U. C wants to pair with J and A wants to pair with U. So you have this string of nucleotides, and the goal here is to find a maximal pairing of these base pairs in a non-crossing way. Okay, so this would be a valid matching, like here G matches with C, A matches with U. But if you had tried to match A with U and this G, if you had tried to match with C here, then there will be a crossing, and that's not allowed. Okay, so you want to find the maximal non-crossing pairings of this nucleotide. So that was the RNA folding problem. Again, this RNA folding problem, you can solve it in you can solve this RNA folding problem in n cube time. So here you would see a little bit of distinction here. Like I'm telling you that you can solve it in n cube time, but the box from where the RNA folding was shown, the lower bound for RNA folding, as you can see, is n to the omega, where omega is the exponent of first matrix multiplication, and you can multiply matrices much faster than n cube time. So, okay, anyway, so let's look at the RNA folding, like how do you solve it in n cube time? Again, you can write basic dynamic programming for it. So you want to know what is the maximum number of pairing possible for RNA folding. So let's look at any substring from I to J. How many such substrings are there? You're looking at every starting point and every end point. So there are n square such substrings. Now you're looking at I to J, and you look at, okay, if I match I to say any L here, and I try to match L plus 1 to any J here, now let's look at what is the maximal pairing possible from I to L and L plus 1 to J. And you add them together. And you do that for every possible such breakpoint L and take the maximum of it. And that will give you the RNA folding. That will give you the maximum number of pairing possible between I and J. Okay, so you're looking at every substring. For every substring, you are looking at the breakpoints. The number of possible breakpoints depends on the length of the substring. And for every breakpoint, you are looking at the subproblem I to L and L plus 1 to J. You have already computed the solution for this subproblem. You are adding them, and you are taking the best of among these subproblems. So what is the time complexity to compute for the specific IJ, specific subproblem I to J? That depends on what is the length between I to J. In the worst case, it could be order of n. And you are again filling up a quadratic size table. So overall, like you have to fill up n square entries. Filling up each entry requires you to look at all these breakpoints. So it can take order of n times. So overall, your time complexity could be order of n cubed. And the space complexity, because it's a quadratic table that you are trying to fill up, the space complexity would be order of n squared. So that's your RNA folding problem. So finally, I will just mention about one last problem, and then we'll see how. So we haven't yet come to the approximation algorithms yet. So we'll come to the approximation algorithms after mentioning this last problem. So the last one is language edit distance. So for RNA folding, you saw that the RNA folding was in the second box where the lower bound was n to the omega, but the dynamic programming solution was n cubed. So there is a gap between the upper and the lower bound. Now the last problem is language edit distance. Here the interesting phenomena, if you look at the boxes that I have shown you, that this problem appears in two boxes, two circles. So both the middle one and the last one. And you'll see there is a little bit of difference here. So this one is saying language edit distance, and this one is saying language edit distance insertion only. So just a little variation. I will mention what this problem is and what exactly this variation is. But the point to emphasize that with a little, even with a slight variations in the problems, they can move from one complexity class to another, obviously under P. Okay, so what is language edit distance? So language edit distance, it's a generalization of string edit distance in a way that in string edit distance, you have one reference string. Now you are given an input string and you are asking how many minimum edits you need to do on your input string so that it looks like the reference string. In the language edit distance, what you have is a collection of reference strings, not just one reference string. You have a collection of reference strings, and now you are given an input string, and you want to make minimum edits on this input string so that it looks like at least one of the reference strings. So you can, whatever the minimum edits will transform this input string to look like any one of the reference string. That's your language edit distance. So this problem obviously generalizes string edit distance because there is just not one reference string here. Now there are a bunch of reference strings here. But this also generalizes context-free grammar in the parsing problem. In the parsing problem, you basically ask, you are given as input string, does this input string belong to the language or not? So you can think about this set consists of the strings that belong to the language. Now you are asking whether this input string is like within distance 0 or not from this collection of strings, whether there exists one string here which is same as the input string. So that's your parsing problem. In the language edit distance problem, you're asking not just the zero non-zero question, but you are asking for the exact distance, exact edit distance. So this problem is very generic. So it's just showing you an example that these strings could all be generated. These strings could all be generated using this grammar. So the parsing problem would ask you whether the input string belongs to this language or not, generated by this grammar, whereas the language edit distance is asking you how many edits do we need to do on this string so that after the edits, this string belongs to this language generated by this grammar. This language edit distance problem, it's a very generic problem because it tries to answer a question of this form, like you are given some model of your data and you are given some model of your data and you are asking whether your input data, it fits that model or not. And if it doesn't fit, then you are asking what are the changes do I need to do on my data so that after the changes, it matches the model. And because it's a very generic problem, it has applications in many different areas. Like in linguistics, you can use this language edit distance to find and correct grammatical mistakes. Like obviously here it's like some language, it should satisfy a certain model. Now, if there are errors, that will be the deviation from that model. And using this language edit distance, you will be able to correct, at least suggest the corrections to your input data. Similarly, language edit distance has applications in compiler optimization for automatically correcting errors in your program. In genomics, in fact, the RNA folding problem that I showed you can be modeled as a special case of language edit distance problem. Finally, like language edit distance, it has by nature, it's related to data quality and data quality management, where you can think about your clean data should follow this particular model. But now you have your actual data, which has errors, which has noise in it, has errors in it, and that's why it's deviating from that model. And now this language edit distance, if you have an efficient algorithm for computing language edit distance, you can use that to suggest automated repairs for your noisy data. That was the motivation from which I started looking at language edit distance problems. So we had some data quality problems in hand, and ultimately the way that we took to correct it is through this language edit distance model. Now, how can you compute the answer for language edit distance? Again, it's a dynamic programming algorithm. It's very similar to the RNA folding dynamic programming solution that I showed you. Its time complexity is NQ, space complexity is N squared. You have an entry for every substring. You are given an input string, right? And for every substring starting from I ending at J, you have an entry in this matrix. And in order to find out what is the language edit distance for the substring I to J, you are looking at all possible breakpoint L between I and J. You are looking at the edit distance from I to L and edit distance from L plus 1 to J, and you are adding them. And then you are taking the minimum over all these L's. Okay, so basically you are looking at, you have to fill up all these N square entries, and filling up each of these entries will require you order of N time. And that's why you again get an order of N cube running time for language edit distance. So here is the scenario, like what I have described so far. In the first box, everything is like, if you have a better than quadratic solution, you will beat, you will refute the strong exponential time hypothesis. Right now, all of these problems, just using dynamic programming, you can have N square running time. So they basically match the lower bound and the upper bound, nothing much to do here in terms of exact algorithms. If I look at the third circle here, these are based on APSP hardness. These are N cube hard. Again, there are dynamic programming algorithms, which matches the N cube hardness. So there is again the lower bound and the upper bound, they match. Whereas if you look at this second box, essentially is RNA folding. So for parsing, this is n to the omega hard, and in fact, for parsing, there exists algorithm that's matches n to the omega. So this is we are fine with this one. But here, there are some problems for which the hardness known is only n to the omega, but the algorithms that were known before 2016 were all in cube, all in their running time are all in cube, and they were based on this simple dynamic programming. So in 2016, we had some results where we were able to improve the running time of these problems from n cube to something better than n cube. So we are still not there to match it at the Boolean matrix multiplication level or to improve the lower bound. And that, in my opinion, is a pretty challenging open question here. Like, how can we breach the gap between the upper bound and the lower bound for these problems like RNA folding, language at a distance? So right now, previously there were no algorithm which had a better than n cube running time. Now we had something better than n cube, but still it's not there at the Boolean matrix multiplication level. Okay, so far I had been telling you about these low polynomial time problems, about these classes mostly between quadratic and cubic, and was emphasizing on like what kind of lower bounds were known for it and basic algorithms like dynamic programming algorithms to solve them exactly. So for some of these problems, even the exact complexity of these algorithms are still not known, like the ones in the middle, where there is a gap between the upper bound and lower bound, but for the rest, we have a pretty good understanding now, like at least the lower bound and the upper bound match. But when we are dealing with large data, it may not be very satisfactory to have, say, n cube running time or say n square running time. So the question is there a way that we can develop faster algorithms when it's highly unlikely that we can do so using like this, if we insist doing returning exact answers? So obviously in this kind of scenario, we have to design approximation algorithms. And trading quality versus speed, like we can, if we are willing to return some solution that is not exact, but very close to exact, there might be hope that we can reduce the running time significantly. And that could be very useful in the context when you have large data. So we would like to understand the approximation versus speed of this trade-off at the finest possible level for these polynomial time problems, like which are, and just see what kind of trade-off is possible, what kind of hardness could be projected for this kind of designing this kind of approximation algorithms. And that's the world of fine-grained approximation algorithms. So basically, fine-grained problems, they all try to specify the true complexity of low polynomial time problems, and approximation algorithms for fine-grained problems are trying to develop even faster algorithms in this low polynomial domain by using approximation. So let's look at for the problems that we have just mentioned, what kind of results we can get using approximation. So for string edit distance, I mentioned that this is a classic example of a quadratic hard problem for which we have a matching lower bound using strong exponential time hypothesis. But if you allow approximation, you can lower the running time significantly. So right now, the best result is from last year, 2020, where the running time has been reduced from order n squared to near linear. It's not order n, but n to the 1 plus epsilon, where epsilon could be arbitrarily small, and what you get is a constant approximation. Okay, so if d is a true edit distance between two strings, you will get within a constant factor of d. Your return solution will be within a constant, will have edits which is within a constant factor of d. So get a constant approximation factor, but you can reduce the running time all the way from n squared to near linear. So that's for string edit distance. For all pair shortest path, this is a result that's been there for a long time now, that using approximation, you can improve the result from n cubed to n to the omega. So this is the exponent of fast matrix multiplication, and you can get a 1 plus epsilon approximation, when epsilon again can be arbitrarily small. And you can reduce the running time from n cubed to n to the omega. There are some other problems like stochastic grammar parsing. This is from my paper, where like we are able to reduce the running time from n cubed to significantly subcubic using 1 plus epsilon approximation. This is another problem. So if I go back again to my circle, so this was one other problem in the middle circle, for which you can write an n cube algorithm, like you can write a dynamic programming that runs in n cube time. But if you allow approximation, you can reduce the running time again to near linear. And here you can get something like log n approximation. But in reality, if we have implemented the approximation algorithms in certain data, and it gives very good performance. Okay, so these are all to show you that using approximation, you can really reduce like the running time from n cubed to linear, from n squared to linear, and so on. So for RNA folding, like you can reduce the running time from n cubed to n squared. It's not so drastic like n cubed to linear, but at least we could reduce the running time from n cubed to n squared, obviously allowing approximation. And I will tell you later what kind of approximation we get for this problem. And for the exact result, this is from the 2016 result that I just mentioned, that we are able to improve the running time from n cubed to subcubic. It's still not like the lower bound for it is like n to the omega with the current exponent. There is still quite a bit of gap here. And that's a big open question to close this gap. Okay, so because this is like an online talk, I'm not being able to see my audience. So maybe let me stop here a little bit and see if there are questions here. So far what I have talked about is really like giving you some examples of problems that are at the heart of fine-grained complexity, fine-grained algorithm design. I've shown you what were their true exact complexity, and what happens if you try to beat their exact complexity. They will either lead to refutation of strong exponential time hypothesis, or it will lead to a better algorithm for all pair shortest path, which will be a breakthrough, which is equivalent to compute mean plus matrix multiplication. And there are some problems in the middle for which we know that at least it's as hard as computing Boolean matrix multiplication, but we are, in terms of designing algorithms, we haven't reached there even for exact design. And then what I've just started to talk about is approximation algorithms, and to show you like some results, and just told you about some results that using approximation, you can get much better running time. Sometimes you can reduce the running time even from n cubed to near linear if we are allowing approximation. And when we have tried experimenting on these algorithms and have seen pretty nice results even on real data when we have implemented these algorithms. Okay, so questions.
I just have a quick question, just to confirm, are these reductions two-way reductions in the sense that if the strong exponential time hypothesis fails, then we could solve longest common subsequence in subquadratic time? And is it the case that the vice versa, if we could solve longest common subsequence in subquadratic time, then the strong exponential time hypothesis fails?
So not all the reductions, I think I mentioned that not all the reductions are both ways, but some of the reductions are. Like the reductions from a PSP and some of the graph problems, those are like equivalent classes, but not, but the others are like more one-way reductions.
I see. Thank you.
Are there other questions? Okay, so if there are no more questions, so let me go into the main topic of this talk, which is about approximation algorithms, and which we are just just to ensure that we are talking about approximation algorithms for polynomial time problems. We name it as fine-grained approximation algorithms, because if you know of approximation algorithms, it's an old topic now, and it has been traditionally introduced to handle NP-hard problems so that you can come up with polynomial time algorithms for NP-hard problems. But when we are dealing with low polynomial time problems, obviously they're already low polynomial time. So here the goal of approximation algorithms to make the running time much faster and to really understand the trade-off between the running time and the quality of the solution. So that's your fine-grained approximation algorithms. So obviously what you can do, you can take each of your favorite problem and can try to come up with some faster way of getting an approximate solution, but that's probably not what you want to do. You want to come up with some generic techniques that you can employ for a large number of like polynomial time problems. So for NP-hard problems, such techniques could be like using linear programs or semi-definite programs. Many optimization, NP-hard optimization problems, you can model them using linear programs or SDPs, and then you can come up with LP rounding methods to come up with these approximation algorithms. So that had been a very like generic way of developing approximation algorithms for NP-hard problems. So the question will be, what could be such generic techniques when we are dealing with polynomial time problems and we want to come up with fast approximation algorithms for them? So all the problems that I have mentioned so far, like we have solved them exactly using dynamic programming. So one generic technique that we might be able to employ here is like you take a dynamic programming and somehow have some way of making this dynamic programming much faster, because most dynamic programming, the obvious drawback of them are that they require and they have either have high time complexity or both high time complexity and space complexity. So those are the obvious drawbacks of dynamic programming. So if there are some generic ways so that you can take a dynamic programming and can make it faster and make it take less space, that would have direct effect on large number of problems, low polynomial time problems. Because if you have a problem and you are trying to solve it, like you just do not know whether it's NP-hard or not, and suddenly you find a polynomial time solution, more likely than not that you found a dynamic programming solution for it. So it's like ubiquitous for solving low polynomial time problems. So what we did, like we took a dynamic programming and we employed two ways to make them faster. One is to use what we call amnesic dynamic programming. So what is amnesic dynamic programming? Well, in a dynamic programming, you try to maintain some states. Okay, so like if you're thinking about, I showed you some dynamic programming tables, they had n squared different subproblems. So you can think about the states represent one of these subproblems, or the states represents when you're trying to solve a particular subproblem, what are the previously computed subproblems you have to look at. So if there is a way to systematically forget some of the states of this dynamic programming, so that's your forgetful dynamic programming or amnesic dynamic programming, then you might be able to improve the running time and even the space complexity of dynamic programming. So that's one way. And the other way is to use fast matrix multiplication. So you take a dynamic programming and somehow massage it in a way so that you can cast it as a fast matrix multiplication problem. And then since you have this better than, for Boolean matrix multiplication, you have this better than n cube running time. So you use that to get better than, say, n cube running time for your problem in hand. Okay, so these are obviously, again, these are not meant to be exhaustive, but these are some way that we have been able to take a dynamic programming and improve its space complexity and time complexity. So let's look at this amnesic dynamic programming first. So it's a way to forget dynamic programming states systematically to make them run, allow for faster running time and better space complexity. So there could be two ways of forgetting. So one could be that when you have a DP table, you do not maintain all these intermediate solutions. You just sample and maintain a part of the DP table. So that could be one way of forgetting states. The other way could be when you are trying to compute a one particular solution, instead of looking at all these different subproblems that you had that you would have done if you wanted to compute the exact answer, instead you forget a few of them and you do not look at few of them and you compute your solution based on a sample of previously computed subproblems. Okay, so that could be another way of forgetting DP states. And yes, so these two could be possible ways of forgetting dynamic programming states and having a better time and space complexity. So what kind of results have we got using this amnesic dynamic programming? Since we're looking at RNA folding and language at a distance, let's just look at these problems. So for exact computation, you have n-cube running time using dynamic programming. Using amnesic dynamic programming, what you can get, you can reduce the running time from n-cube to n-square. It comes with an additive approximation of epsilon n. So this epsilon doesn't need to be constant here. Epsilon could be anything. So for example, you can put your epsilon to be say 1 over square root of n. Then your additive approximation will be square root of n, and the running time will be, instead of n cube, it will be n to the 2.5. Okay, so similarly for RNA folding, and there is a reason why you'd see similar results for language edit distance and RNA folding. As I mentioned, that RNA folding can be seen as a special case of language edit distance. So basically, the results are kind of similar here, but there could be scope of improving the RNA folding result even further because it's a special case of language edit distance, and that's another open question that would be very nice to have better than what we know for language edit distance for RNA folding. Okay, so these are the kind of results that we can get. Like with epsilon and additive, you can reduce the dimension by 1, like from n cubed to n square using epsilon and additive approximation. And this amnesic dynamic programming could also be very effective in terms of space complexity. So here, remember all these dynamic programming solutions, they require to keep this entire DP tables, and that has n square space complexity. Now using this amnesic dynamic programming, you can reduce the space complexity from n squared not to sublinear, like you can reduce the space complexity to n to the 2/3, again with this epsilon and additive approximation for language edit distance and RNA folding. For string edit distance, you can reduce it to square root of n and so on. And moreover, this amnesic dynamic programming, it also comes with some other benefits, like it allows for dynamic programming is generally very sequential in nature. Like you have to compute the smaller problems first because your larger problems depends on the smaller problems and so on. So it's a very sequential nature. But because of amnesic dynamic programming kind of reduces the interdependence between the subproblems, it also allows for faster parallel implementation. So you can implement many of these amnesic dynamic programming algorithms in the MapReduce framework or in streaming framework, and that will give you like sublinear pass algorithms for all these problems. If you have an amnesic dynamic programming solution, you can transform it into a sublinear pass streaming algorithms or efficient MapReduce algorithms. Okay, so let's look at the RNA folding problem, and let me tell you how you will design this amnestic dynamic programming for RNA folding. You will use a similar kind of technique for language edit distance as well. So for RNA folding, remember what we do. We look at every substring from I to J. And then what we do, we look at the breakpoints L between I and J. We look at how many maximum number of pairs can be matched from I to L. How many maximum pairs can be matched from L plus 1 to J. We add them. And then we try every possible breakpoints and take the maximum. And the running time of order n cube just comes from considering this order n breakpoints corresponding to order of n square subproblems. So one way you can think about improving the running time is that when you are considering this order of n squared different subproblems, don't look at all these n breakpoints. Maybe look at only log n breakpoints corresponding to each of these n square subproblems, and instead of order of n cube, your running time will become n square log n. Okay, so that's basically using the second principle of amnestic dynamic programming, which is saying when you are computing each of these subproblems, you look at fewer subproblems that you have computed before. Okay, so that's like, and that way you can improve the time complexity of your dynamic programming. So the question is, well, this is pretty easy to say that, okay, I will look at only log n subproblems instead of looking at n subproblems. But the question is, how am I going to select these log n subproblems? So the very first attempt could be that instead select these log n subproblems out of these n subproblems. Here each subproblem is represented by this breakpoint. So select this log n breakpoints out of this n breakpoints as uniformly at random. So if you do that, unfortunately, that will not lead to any good solution. So you will get an error of order of n, which is pretty useless. So it will just not work. So uniform random sampling is not a good idea. And irrespective of how does your recursion looks like, dynamic programming is all about solving a recursion, right? So it doesn't really matter how your recursion tree looks like. Uniform random sampling will not give you a good result. So the second idea might be like if your recursion is somehow balanced. So if it's a balanced recursion tree, where in the leaves you have these small subproblems that you are trying to solve, and as you are moving up on the tree, you have bigger and bigger subproblems that you are solving. So if your recursion tree is balanced, then as you can see, there are many leaves here, right? So there are many more leaves like compared, so you're solving many more small subproblems than large problems. So one idea might be that make small errors on smaller subproblems, and since you are not solving too many large subproblems, you can allow some errors in these larger subproblems. So maybe your error should be proportionate to the size of the subproblem that you are solving. Okay, so if you try to do something like that, then indeed you can do well on if your recursion is somewhat balanced. But if your recursion is completely unbalanced, where you have like these leaves, you have as many short subproblems as long subproblems, then you will again be in water and your error will still be order of n. So sampling based on like shortest, so if you have smaller subproblems, sample at a lower rate, and if you have larger subproblems, sample at a higher rate is a good idea only if your recursion tree is somewhat balanced. But if it's not, then that idea will also fail. So we cannot really sample based on the length of the subproblem. But then what can you do? So this is the third idea. And that basically comes from looking at these two extremes. In one hand, you have a completely balanced recursion tree, and in the other hand, you have a completely unbalanced recursion tree. So in both cases, you see in this balanced recursion tree case, you have a lot of small subproblems. So if you can somehow not make too much errors in the small subproblems, you might be able to bound the overall error. And in this long recursion tree, what you see is that whenever you have a small subproblem and a large subproblem, so it's really like you are considering a breakpoint which is very close to the boundary. So you're creating a small subproblem only when there is another associated long problem. So your breakpoint is very close to the boundary. Okay, so this observation leads to the third way of sampling, which works out pretty well for us, where you are saying that you are trying to sample breakpoints. So sample breakpoints at a much higher sample rate when you are at the corner, and your sampling rate diminishes as you are going into the middle. So you are looking at I to j, and you have to sample your breakpoints right here. When you are considering exact solution, you will consider all the breakpoints, and there are order of n of them. Now you want to consider only log n breakpoints. So how are you going to do that? So you will break this interval into these small parts, into these windows of say length k. In the first window, you will take all the breakpoints. In the second window, you will take half of the breakpoints. In the third window, you will take 1/4 of the breakpoints, and so on. And similarly, you will do starting from I. So you will look at the first window of size, say length k. You will consider all the breakpoints here. In the next window, you will consider half of the breakpoints. In the next window, you will consider 1/4 of the breakpoints, and so on. So if we look at the overall sampling probability of the breakpoints, this is what is happening. So here you are sampling the breakpoints at a much higher rate. And as you are going in the middle, your sampling rate is becoming much lower. So you are sampling much fewer breakpoints as you are coming into the middle. So if we look at this kind of sampling probability, so if you have a small subproblem, like I and j is the length is really small, then what happens? Since you are sampling at a very high rate in the boundary, it's a small subproblem, so you're going to sample breakpoints at a very high rate for small subproblems. So that will kind of handle the case of balanced recursion tree. And if you have a large subproblem, then what happens? Like your breakpoint is somewhere close to the boundary. And because you have a very high sampling rate, then it's very likely that you will be sampling that breakpoint. So even for long recursion tree, therefore, you are not going to make much mistakes, because most of the cases your breakpoints are close to the boundary, and there the sampling probability is so high that you are likely to sample that breakpoint. So that's kind of the two extreme cases. Obviously, just handling two extreme cases is not enough, but that gives you some idea like why this kind of approach for sampling probability just works out. So for RNA folding, it will look like this. Again, like you have high sampling probability at 2 ends, low in the middle. Similarly for language edit distance, there are some one-dimensional problems. So this RNA folding, language edit distance, these are like two-dimensional problems. For one-dimensional problems, your sampling probability generally looks like this, that it's high at one end and it's just going down. So you can think about for higher dimensional problems, what could the sampling probability look like? It somehow it gets sparser as you're going in towards the centroid, and it's like much dense as you are towards the boundary. And as here is the intuition that I just mentioned already, that when you have this short recursion tree, you can make mistakes on the long subproblems because there are not too many of them, but you really do not want to make mistakes on these short problems. And just the way the sampling probability is selected, you are not going to make too much mistakes on the short subproblems. So that's why it handles this short recursion tree. And for the long recursion tree, since again, these short problems are created when the breakpoint is towards the boundary and we have a much higher sampling rate towards the boundary. So this kind of scenario is also handled pretty well in this when you are sampling in this nature. So sample based on the position of the breakpoint, and that gives you a very good result. So the next question is, okay, so amnestic dynamic programming, you now might have a dynamic programming problem on your end, and you are wondering whether can I apply this amnestic dynamic programming and make it run faster. So what properties does your problem need to have so that you can employ this kind of sampling techniques, like this kind of sampling techniques to make it run faster? And the answer, obviously, there could be some other properties as well, but this amnestic dynamic programming specifically will work for any problem that has this Lipschitz property or a continuity property intrinsic in their problem. So if you're thinking about RNA folding, what is RNA folding problem? You're trying to maximize the number of pairs of base pairs in a particular string that can be matched. So if you just increase your string by a little bit, right? Suppose you add a few more symbols to the end of your string. So how much your answer is going to change by this little increase in your input length? Not by much, right? So there is this continuity in your problem, it's intrinsic in your problem. So any problem that has this Lipschitz property, has this continuity property, you will most likely be able to apply this amnestic dynamic programming technique and get a much faster running time. And indeed, like this Lipschitz property seems to be very fundamental when you are trying not only to design faster algorithms, but also to come up with lower bounds. As I mentioned, that language edit distance is this like interesting problem which appears in both these circles, like one which is for Boolean matrix multiplication hard problems, and the another one which is this APSP hard problem. And there is a small difference here. One is saying insertion only, which means you only allow insertion as your edits. And the normal language edit distance will allow for insertion or deletion or substitutions. In fact, what happens, like when you move from language edit distance to language edit distance insertion only, you lose the Lipschitz property. So language edit distance exhibit the Lipschitz property, this continuity property. But language edit distance, when you're restricting the types of edits, when you're just allowing insertion, does not have this Lipschitz property. And because of that, it becomes like, it moves from one class to another. It becomes much harder. So when you have this Lipschitz property, it makes it much more amenable to design faster algorithms. And that's basically what we exploit. If you look at the proof, that's exactly the property that we exploit to come up with a fast, to show that this amnestic dynamic programming works. So if you have a problem, if it has this continuity property, generally most string problems will have this continuity property, then you can employ these amnestic dynamic programming and get a faster running time and also get faster, much better space complexity. So I haven't shown you how it works to get better space complexity, but you can look at the paper. It just not improves the running time, but also the space complexity. And in fact, for space complexity, the reduction is even more dramatic, that it reduces from n squared to sublinear. Okay, so that was one way of taking a dynamic programming and making it faster. So the other way that I mentioned is to take a dynamic programming and somehow massage it to convert it into a matrix multiplication problem, and then use that matrix, faster algorithms for that matrix multiplication to come up with a faster solution. So let's again look at this RNA folding problem, and let's see how we can take the dynamic programming and can massage it into a matrix multiplication problem. So remember what we are doing for RNA folding, like we look at this substring starting at I, ending at J. We want to compute that. So we look at this breakpoint L. So we look at what is the RNA folding solution for I to L. We look at what is the RNA folding solution from L plus 1 to J. If this is X and this is Y, then in order to come up with the RNA folding solution for I to J, I will just add up these X and Y. Right? What is the solution from I to L? What is the solution from L plus 1 to J? I just want to add up X plus Y, and then I will look at all this possible L and I will take the max. That's your RNA folding problem. And this is, in fact, as you can see, this is like max plus, or if you are looking at language edit distance, in this max will be mean. So that will be mean plus. So essentially you are considering, you can view this computation of this dynamic programming table as computing mean plus product or max plus product. Okay, so basically you will start with some known solution for the diagonals, which is just for substring of length 1. And then you will keep on computing either mean plus or max plus product. And you will compute the transitive closure of this mean plus or max transitive closure of this mean plus or max plus matrix multiplication. And at the end, you will, whatever the solution you will have, you can show it that is exactly same as what you would have computed otherwise using the dynamic programming. So essentially this dynamic programming solution, or you can view it in this just slightly in a different way using this mean plus matrix multiplication or max plus matrix multiplication, they are equivalent, to come up with their exact the exact solution. So now, like, this is okay. Like this really states the problem, like saying instead of dynamic programming, you can converting it into this mean plus or max plus product. But just saying this is not going to help you to come up with the fast solution. Because as I mentioned previously, that these are semi-rings, and over semi-rings, we still do not have an algorithm that runs in time better than n-cube. And indeed, if you can have a better n-cube running time for min plus max plus, you are going to break the APSP conjecture. So that's going to be a huge breakthrough. So then what can you do about it? So again here, like, the Lipschitz property becomes very useful here again. Like, it's not only that these problems have Lipschitz property in them, but when you are coming up with these matrices that you are trying to multiply, this Lipschitz property in these problems get translated into these matrices as well. So if you look at the numbers that are being generated in these matrices, you will see that if you look at particular entries, consecutive rows or consecutive columns, their difference will remain bounded. It's again coming from the problem, but it gets translated into these matrices. So these matrices, you are trying to do mean plus product or max plus product. For arbitrary matrices, this mean plus or max plus product is going to take you cubic time. But for these particular problems, because they had this Lipschitz property, this gets translated into these matrices, and you will see this Lipschitz property in these matrices as well if you're looking at entries in the consecutive rows or consecutive columns. And using this Lipschitz property, what we are able to do is to give an algorithm for mean plus product, that when the matrices have this Lipschitz property, you can get better algorithm even for exact solution. So you can get exact solution in less than subcubic time, and you can utilize this Lipschitz property even further for approximation algorithms and can get a result very close to n to the omega when you are allowing approximation. But you have to utilize this Lipschitz property. So this Lipschitz property somehow is central for getting this faster algorithms, whether it's through amnesic dynamic programming or through this lens of fast matrix multiplication. So Mahmoud, how am I doing about time? How much time do I have? And it's also a good time to stop and ask questions. So do I have, can someone tell me how am I doing with the time?
Well, this session lasts another 45 minutes, so we are not at all in a hurry.
Okay, very good, very good. And are there any questions? If no questions, then I will move on. So far, let me just summarize what I had been telling so far. So far I was looking at how you can design, how you can design some systematic way of for polynomial time problems. What could be a systematic way to develop approximation algorithms? So for polynomial time problems, mostly you will be solving it using dynamic programming, and the dynamic programming generally has very high space complexity or high time complexity. So it's natural to ask for techniques that you can utilize to make your dynamic programming run faster or to save space. And I just told you about two ways of doing that. One is using amnesic dynamic programming, and another way is to take a dynamic programming and convert into convert it into computing matrix multiplication over some algebraic structure, and then utilize that to design faster algorithm for those matrix products. And we saw that using these, like for some cubic problems like RNA folding, like language edit distance, you can improve the running time from cubic to quadratic using approximation algorithms, using like allowing approximation. Like you can reduce from n cube to n square by allowing additive approximation epsilon n for using amnesic dynamic programming. And the other way, like taking a dynamic programming and converting it into fast matrix multiplication, even for exact, you can get better than n cube running time even for exact versions of it. And if you allow approximation, in fact, you can reduce the running time much farther. For the amnesic dynamic programming, you just not get the advantage of time complexity, but you also get the advantage that it gives you savings in space, because dynamic programming generally have to maintain all the states, and that's why it becomes very like high space complexity. But because in amnesic dynamic programming, you are just keeping a few of the states, you are forgetting many of them. So it also comes with the added bonus that it has low space complexity. Okay, so far I had been dealing with cubic problems and reduce their time complexity, and showed you how to reduce their time complexity from cubic to subcubic. So let's look at another problem when we can get a much higher speed up, like from cubic to linear time. Okay, and let's see how we can what is the underlying technique that we use to do that. So amnesic dynamic programming generally is useful to reduce the dimension by 1, like from n cube you reduce it to n square, or maybe from n square you reduce it to ln n. But it's at least like so far we haven't been able to reduce the running time beyond this 1 dimension using amnesic dynamic programming. So if you have to reduce from n cube to linear, somehow you have to have some other way of coming up with the algorithm. Okay, so let's look at one problem. So
excuse me, Barna, may I briefly interrupt you? We have a question in the Q&A area, so maybe you want to answer that question. Sure. Can you see it, or do you want me to read it?
I cannot. I cannot see it. Can you read it?
Okay, so it's by Yiwen Zhu, and it reads, "Thank you for the talk. Could you explain a bit how the epsilons represent? Are those related to the approximation errors or bounds?"
Yeah, okay. Yeah, that's a good question. The epsilons are related to both approximation and the time complexity. So that's kind of the trade-off parameter. Like so for amnesic approximation, let's go back to the slide maybe. So here, as you can see, the epsilon is both in the approximation factor and also in the running time. So if you are increasing your epsilon, or say if you are decreasing your epsilon, then your approximation factor is getting better and better. But decreasing epsilon means your running time is getting higher and higher. So that's your the trade-off parameter. Okay, so the epsilon really comes up both in the approximation factor and in the running time. And the dependency of epsilon here, this is specified here for like how the dependency is. There's a linear dependency on the approximation factor and the time complexity. Now, when you are looking at the other, the using converting a dynamic programming to computing fast matrix multiplication, the dependency may not be so nice. Like it could be like it's a quadratic dependency and so on. So you can take a look at my yeah, so for exact algorithm, there is no dependency. It's just for the approximation algorithms that there is a dependency. So for amnesic, it's like linear. And I think for fast matrix multiplication, the dependency is quadratic. Like, so that's, and there you can get multiplicative approximation. So you get 1 plus epsilon multiplicative approximation, and your dependency in epsilon is say 1 over epsilon square. Okay, so there is always this trade-off, and that's that, and epsilon is your trade-off parameter, that how much you are trying to balance between the error and the running time. Does this answer your question? So they cannot ask.
Yeah, it's yes, thanks.
Okay, thank you. Okay, so let's look at a problem for which we can get a much better speed up. That is, so we'll see how to reduce the running time from NQ for exact algorithm to linear when we are allowing approximation. And this is a problem again, if you remember those circles, it's from the second circle, which is into the omega hertz. So you cannot design an exact algorithm which is better than in running time, better than Boolean matrix multiplication. We do have exact algorithms for it now, which has better than cubic running time, but it still doesn't match the lower bound. So that's an big open question here. And what I'm going to show you is an algorithm that allowing approximation will reduce the running time from n cubed to near linear. Okay, and this problem is called Dyke edit distance. So it's very similar to RNA folding. So in RNA folding, remember there are these 4 base pairs, C pairs with G and A pairs with U. So both this kind of pairing, AU and UA are valid. So you can pair whether A comes first or A comes later, it doesn't really matter. You can pair A with U in any order you want. So in Dyke language, there is a notion of open parenthesis and close parenthesis. So this is matching, but this is not matching. So that's the only difference. So you can think about this is okay, AU is okay, but UA is not okay. So that's the only difference between Dyke language and RNA folding. So in Dyke language, there is this notion of open parenthesis and close parenthesis, which is not there in RNA folding. And this Dyke language, it comes up almost in many different contexts. Like if you're thinking about LaTeX, you have begin equation, end equation. So whatever you want to begin with, you have to end it. Look at XML, look at HTML. Like you have anything like you opening up, you have the open parenthesis, you have to have the close parenthesis. And this Dyke edit distance is in fact a generalization of string edit distance. Like string edit distance, you can think about, you have 2 strings. So you can think about one string is entirely of open parenthesis and the other string is entirely of close parenthesis. If they were both the same string, then you could have matched all the open parentheses with the close parentheses. So, and you would have got like 0 string edit distance because they are both the same string. But that's the way you can view string edit distance as a Dyke edit distance problem. Okay, so Dyke edit distance is a much more general problem than string edit distance. And for when it comes for XML errors or HTML errors, actually Google pointed out that the mismatches between opening and ending tags is one of the second largest contribution in XML errors. And there are different mechanisms to solve these problems, this mismatch between open parentheses and close parentheses. There are many greedy heuristics that generally are employed by different browsers. And you can also have this edit distance based repairs. In fact, we did an experiment, this is long time back, 7, 8 years back, that we did some experiments on XML files to see how edit distance based repairs perform compared to these greedy heuristics to fix this open and end mismatches. And we saw that edit distance based repairs uniformly perform much better than these greedy rules that are employed by internet explorers and so on. Okay, so now the question is, like, I already showed you how to well, for Dike language edit distance, again, if you want to solve it using dynamic programming, it's exactly same as the RNA folding dynamic programming. Okay, so like you take a substring I to j, there are n square such substrings. You want to solve for each substring. You look at all the breakpoints L between I and j. There are order of n breakpoints, and you want to find like you want to minimize. You are trying to minimize the number of errors, number of non-matched parentheses. So you want to delete them, and rest should match up perfectly. So you're looking at all breakpoints L. You look at I to L. You look at L plus 1 to j. You see whether what is the solution for those two. You add them up. You take the minimum over L, and that's your Dike edit distance. Okay, so n squared subproblems for each of them, you have order of n breakpoints, so your n cube solution is there. And so that's the dynamic programming. But now we want to have a solution that will run in linear time. So the question is like, okay, so what could be the starting point for a linear time algorithm for this Dike edit distance? Well, if I ask you this question, suppose I give you a string of parentheses, and I ask you, does this string have Dike edit distance 0? How would you solve it? So that's actually a very easy question. Like what you would do, you can use a stack. Whenever you see an open parenthesis, you enter it into the stack. And when you see a closed parenthesis, what you do, you try to match it with the top of the stack, and it needs to match. If its Dike edit distance is 0, you'll just match it. Right, so this is exactly the question that maybe you have seen it in your first undergraduate algorithms class, that is, you are given a string of parentheses and you want to know whether that's totally well balanced or not. So that's if it's totally well balanced, that's your 0 Dike edit distance. Okay, and otherwise you are basically asking what are the minimum number of parentheses I want to delete, so that after the deletion I have a well balanced parenthesis. So that's the Dike edit distance question. So from 0 Dike edit distance, there is a natural algorithm that pops up that, well, again, I am going to, whenever I see an open parenthesis, so suppose let's take this as an example. So here, these capital letters are open parentheses, and the small letters are closing parentheses. Okay, so capital B should match with small b, capital C should match with small c, and so on. So what you will do, whenever you see the open parenthesis, you will have a stack, and you will just put it in the stack. So you see capital A, you put it in the stack. You see B, B, C, you put it in the stack. Now when you see the closing parenthesis small b, if it were Dike edit distance 0, then this should have matched with the top of the stack. Right here, we are trying to compute the distance. It may not be 0. So I'm trying to compute the distance. And I see they do not match. So I have to decide which one shall I delete so that I can make progress. Right? So one very simple way for deleting one of the symbol could be just tossing a coin. So you toss a coin, and based on if head appears, you delete the top of the stack and try to match the small b with the next symbol in the stack. Or if a tail comes, you delete the small b and you move to the next symbol in your input string. Okay, so basically whenever there is a mismatch, you toss a coin, and based on the decision of the coin, you decide whether to delete the top of the stack or to delete the symbol and process the next input symbol. So that's your random deletion. So here might be you decide to delete this capital C, then this B will match with capital B. This matches, so then you move to the next symbol D and B, they don't match. Again, you toss a coin, maybe you delete D this time, then you read this next B. This small b now matches with capital B, and after that this small a matches with capital A. You are left with some symbols here, like then you will proceed in this way, okay? So like you will again have capital D, will include it in the stack and so on. And at some point, if the stack is empty, but you have left with some closing parentheses in your input string, you will delete all of those. Or if you're exhausted going through the input string, but there are still some string elements in the stack, you will delete those elements from the stack. So that's a very simple algorithm. It's of course linear time because you were just processing all the symbols once, and that's it. Every time when you get stuck, you are deleting one of the symbols. So it's basically just like 2n computation. You can solve this. You will be done with this algorithm. So obviously the question is like, it seems it's a random deletion. The question is how well does it perform? It seems like a very basic algorithm, like it just tosses a coin and makes a decision based on that. Is it any good? Well, let's see how we can analyze this kind of random deletion process. So first of all, first thing to observe that you could have viewed there is an optimal algorithm, right? Like which knows what deletions to perform. And that optimal algorithm could have used this similar kind of stack-based method where it inputs all the open parentheses in the stack. And whenever it sees a closed parenthesis, like if they do not match, the optimum algorithm just knows which one to delete. Like it's not going to make any mistake. It will know, I have to delete this capital C and then I will delete capital C. But here in our process, of course, I do not know the optimum algorithm, what optimum algorithm would do. So I have to make a guess, and I'm guessing based on the coin toss. So with probability half, I will do the same thing as the optimum algorithm. So I will be good. Otherwise, with probability half, I can make a mistake. So if I make a mistake, however, like if I do not make a mistake, if I do the same thing as the op does, then I remain synchronized with the optimum solution, and I'm in a totally good shape. But if I make a mistake, and then I will be going away from my optimum solution, and once I goes away from my optimum solution, I could be getting stuck in different places where my optimum algorithm wouldn't have got stuck. Okay, so I could have my states where I get stuck and I have to make guesses could be very different from where optimum algorithm would get stuck and would make a decision to delete. But luckily, we could still show two properties. So one is, again, these two properties are like very intuitive. So that first property is that, like, whenever I'm getting stuck, there is one of those like deletions. I have to delete either the top of the stack or the symbol that I'm reading from my string. And at least one of them will take me closer to the optimum solution. So there is some optimum solution. Optimum solution is doing some execution. So when I'm getting stuck, there would be one way, either by deleting the top of the stack or by deleting the current input symbol, I will go closer to my optimum solution. So there is always a right move. There is always one correct move. And if I take that correct move with probability half, because I'm not biased, I'm tossing an unbiased coin. Okay, so at every step where random deletion performs the deletion, there is a synchronizing move that moves, and it's move taken with probability at least half. So it takes me closer to the opt. And the another property is locally repairable. Like if I make a mistake, suppose in here, optimum solution deletes this capital C and mistakenly I delete this small b. If I delete this small b, so what the optimum solution does? Optimum solution deletes this capital C and then it matches the small b with this capital B here. Now I have mistakenly deleted this small b. Now, in order to recover from this error, what I really need to do, I need to delete this capital C and delete this capital B. So for every mistake, I can recover and after that, I will be in a similar state as opt. So basically, for every mistake, I can somehow undo that mistake by taking 2 steps. Okay, so these are the 2 properties that this random deletion has. And if you think about a little bit about this, like it will be clear that this process of deleting symbols by random deletion is exactly same as performing a one-dimensional random walk, which is known as gambler's ruin. So what is gambler's ruin? That it's this problem is as follows: that a gambler enters a casino, say with $100, and at every step it can either gain $1, it plays a slot machine, either it gains $1 or it could lose $1. And the question is how many steps, how many times it should play the slot machine so that it gets ruined, that its entire amount vanishes, so it goes to 0. Okay, so think about it like you starting this random deletion process. You have some budget of D. This is exactly the number of deletion that an optimum algorithm would perform. So that's a minimum number of deletion required. Okay, so suppose you are entering with that budget D. At every time with probability half, you do what the optimum algorithm does. So you decrease your you move towards reduces your budget from D to D minus 1 with probability half, then D minus 1 to D minus 2 with probability half, and so on. But if at any step you move from D to D plus 1, then there are 2 steps that you have to take in order to come back to D minus 1. So for every mistake, you have to do 2 correcting steps. So basically these are equivalent. This random one-dimensional random walk and this random deletion process. And once you see this equivalence, then analyzing this one-dimensional random walk is not so difficult. So you can just analyze this one-dimensional random walk and connect these 2 processes and get a bound on the number of errors, number of edits that your algorithm is going to do when the optimum algorithm is doing just D edits. Okay, so the number of deletions is exactly same as number of steps taken by the gambler to get ruined when it starts from $D. And what is D? The D is the optimum number of edits, a minimum number of edits that an optimum algorithm will perform. Okay, so and from there, if you now analyze your one-dimensional random walk, you will see that you get a D approximation. So again, what does this D approximation means? It means that if your optimum algorithm, if it makes D errors, then your algorithm is going to make at most D squared errors. Okay, so or D approximation, so D times D errors. Okay, so D versus D squared. And in fact, we did some experiments, and this is so this white bar is for the optimum errors, and this green bar is for this random deletion. And it's not that good because the D factor D is quite a bit, but still it's obviously always within this order of D bound, and it's in fact better than order of D bound, but obviously like there is a yeah, so it's like 15 versus 55, so obviously much better than factor 15 here, but maybe you are not happy by just being from 15 to 65 and you want to do better. Okay, but still the random deletion is a nice starting point, that it gives you this very simple algorithm, which almost like elementary, that every time you get stuck, you are just tossing a coin and making your decision to delete based on the performance of your based on the outcome of your coin, and that already gives you some results, some approximation results. So the question obviously will be here, like, I don't want an order of D approximation. Ideally, I probably want a constant approximation, and the next best to constant is a logarithmic approximation. So can I reduce my from order of D approximation to say order of log D approximation? And the answer is yes, you can do that. still maintaining near linear time. So time complexity will increase just from order of n to order of n log n, and your approximation bound will decrease from order of d to order of log d. Okay, and how do you do that? You will employ this random walk technique, but instead of doing this random walk once over this entire string, you will break it into smaller, like you will perform many random walks in parallel into short substrings. And by combining these random walks together, somehow in a clever way, you can improve the approximation bound from order of d to order of log d. And indeed, this method of using random walk has been useful for many problems in this area, like from embedding results from edit distance to Hamming distance. There are other problems, very related problems, like for document exchange, various communication protocols, where this random walk based idea has been very useful there to reduce so in those cases, the main one of the bottleneck is to reduce the space complexity. So and these random walk based methods had been useful to reduce the space complexity as well, to design for better streaming algorithms for edit distance and so on. This random walk based methods has been useful. Okay, so there are a lot of follow-up works that has happened using this technique. And this is just a chart showing you that this yellow bar is the performance for your random deletion or random walk method, which is better than order of d factor, but maybe like you want to do, maybe this factor is still not satisfactory and you want to perform better than what your random deletion does. Since I have time, let me actually explain you how to improve the approximation factor using random walk. But this time I'm not going to do the random walk or not going to do the random relation in the entire string just blindly, but I will be employing this random walk method in like shorter substrings. Okay. So let's see how we can do that. So let's first consider a very simple case where you have one sequence of open parentheses. Remember these capital case letters, uppercase letters indicate open parentheses, and the lowercase letters, they indicate closed parentheses. So let's consider you have just these sequence of open parentheses, one sequence of open parentheses, followed by one sequence of closed parentheses. So now I ask you, what is the die-edit distance of this sequence? And we can call this a block, okay? So one sequence of open parentheses followed by one sequence of closed parentheses, let's call it a block. So suppose you have this single block and I ask you, what is the die-edit distance? How are you going to solve this? Well, this is actually a case of string edit distance. So what you will do, you will consider this open parenthesis as your one string and consider this closed parenthesis as your second string. And then you just take this open parenthesis, make it small letters so that they become same. And then you just, since here you are trying to match this C with this adjacent letters here, then this B with here and here, like what you will do, you will take this so you're taking these uppercase letters, you're forming a string from there, you're making them lowercase, and then you will just reverse it. So you have A, B, B, C, then you just reverse it, it becomes C, B, B, A, and now you compute the string edit distance between C, B, B, A and these others, and this B, D, B, A. Okay, and that's going to be your, and you just allow deletion, and that's going to be your die-edit distance. So basically what I'm saying is, if you have a single block, if you have just one sequence of open parentheses followed by one sequence of closed parentheses, then you can just employ string edit distance algorithm and can solve the die-edit distance. So the main hardness of die-edit distance actually happens Because we just don't have one block, we have many blocks. And when you have many blocks, it's not so easy to find out like, okay, like this should be string 1, this should be string 2, and so on. So it's difficult to find the appropriate sequence of open brackets, which should be compared against appropriate sequence of closed brackets. For one block, it's easier because you are just taking the open parenthesis, that's your one string. You're just taking the closed parenthesis, that is your second string, and you are done. But when you have multiple blocks, it's not at all clear how you would know which sequence of open parentheses should be compared against which closed parentheses and so on. So for this particular string, this should be, if you look at these symbols in the red, essentially you should create one, these capital letters should be your one string, these small letters should be your second string. So that should be compared for string at a distance comparison. Then the next will be, you consider these EACC as your another string for your string added distance computation, and this small letters should be your second string for string added distance computation. So that should be the second one, and the remaining should be the third one. But how are you going to know that, okay, so these BBAC needs to be compared with AABB and so on, right? It's difficult to find out these exact boundaries, like where this open parenthesis should be compared with the closed parenthesis. So now what we're going to do, like how can we identify these sequences? It seems pretty difficult to identify these sequences. And the answer is we are going to use the same random deletion process or the random walk method that I just told you now to find out these sequences. Rather than employing it to perform deletion, I'm going to try to find out these sequences, these sequences, and then after I have found these sequences, I'm going to convert this into string added distance problem and solve it. Okay, so that's going to be my recipe here, that I am going to use random deletion to find these sequences, and after I have detected the sequences, I know that I can convert it into a string added distance problem, and I'm going to employ the string added distance problem in each of these three sequences, and I will be done. Okay, so how do you find these sequences? So what I will do, I will start my random deletion process. I will enter the open parenthesis into the stack. I will start with the closed parenthesis. I will try to match it and so on. Now let's look at this string here. So I will first decompose this into blocks. Okay, so what is block? Remember, the block is just one sequence of open parenthesis followed by one sequence of closed parenthesis. So what is block 1? This is the one sequence of open parenthesis followed by one sequence of closed parenthesis. So that's my block 1. Okay, so this is my block 1. What is block 2? This second sequence of open parenthesis followed by second sequence of closed parenthesis. That is my block 2. What is my block 3? Third sequence of open parenthesis followed by third sequence of closed parenthesis. That is my block 3. So I have 3 blocks here. So I'll start my random walk process, random deletion process, just like I did before. And I will continue doing so until I reach this boundary of block 1. When I reach this boundary of block 1, I will stop my random deletion process and I will extract one sequence out of it. Okay, so after I'm done extracting the first sequence, I'll again continue the random deletion process until I hit the boundary of block 2. Once I hit the boundary of block 2, whatever elements I have touched, I will extract the second sequence from it, and that will be my second sequence, and then I will continue until I hit the boundary of block 3 and so on. Okay, so suppose like I start my random deletion process. Now when I hit the first boundary of block 1, the open parenthesis that I have touched is like the CAABBA. Okay, in that case, my first sequence that I have extracted is here, like this CAABBA, and this is the until the boundary of block 1. After I'm done with this, I will continue my random deletion process until I hit the boundary of second block. Now, when I hit the boundary of second block, the open parenthesis that I have touched might be capital C, and go here, E, and all these A's. So now my second sequence is here. Okay, so this got 3A's, E's, double C, then the whatever is the small parenthesis, lowercase parenthesis in the second block, and so on. Okay, so basically I'm just looking at when I'm hitting the boundary of a particular block, and when I'm hitting the boundary of a particular block, what are the open parentheses I have touched, and that's how I'm forming these sequences. And once the sequences are formed, what I'm going to do, I'm not going to look at what the random deletion has done in those sequences. I'm rather going to convert it into a string edit distance problem and perform string edit distance algorithms on them. So now by doing so, what happens to the approximation factor? So here there are 3 blocks, right? And I'm doing these random walk on these blocks. And now I make some errors in block 1. So what happened in the block 1, I mistakenly grabbed this capital K. The actual sequence I should have formed is this one in the below, right? But I have extracted this capital A mistakenly. This capital A should have been should not have been there. But because I've extracted this capital A out, like this capital A is out from here. And because of that, this error kind of propagated in this when I'm trying to extract the second sequence. So error propagated from the first sequence to the second sequence. And because of that, I grabbed 3 other symbols, which should have been here on the third sequence. So what is happening? The error is propagating from first block to the second block, then error is propagating further to the third block, and so on. So error propagates equivalent to the number of blocks that are there in the string. So the string has, say, Z blocks, then the error will propagate Z times, and it can be shown that the approximation error will become order of Z. And each block, you can pre-process it so that each block will have at least 1 error. So the number of blocks, the Z, what I'm saying, is always less than the optimum number of errors. So previously our approximation factor was order of D, where D was the optimum error. Now this approximation factor will reduce from D to Z, where Z is the number of blocks. So basically now instead of order of D approximation, you will get the approximation factor reduces to number of blocks. And number of block is always lower than this order of D. And this is this orange bar here. As you can see that these kind of this random walk now, this refined random walk already performs much better than the first just vanilla random walk method. Just by breaking the random walk in each boundary of the block and extracting a sequence out of it, and then running the string edit distance over these sequences already performs much better than if you had done it just over just the vanilla random walk. So that's the orange part. And the reason why this factor Z, or the number Z is the number of blocks, comes in the approximation is exactly because, like, you make some mistakes in extracting the first sequence, and that mistake propagates to the second sequence. And then the mistake accumulates and propagates to the third sequence, and so on. And this accumulation happens Z times, and therefore you get a Z approximation factor when you are designing the approximation algorithm. So the question here is, how can I stop this error propagation? So is there a way that I can stop this error propagation from propagating Z times, like number of whatever the number of blocks you have? So how can I stop the error propagation with Z times? Okay, and the answer is somehow I have to keep these errors local. Somehow I cannot affect whatever mistakes I'm doing. So there will be some errors. There will be some errors when I'm trying to extract these sequences. But I really did. Mohammed, do you have any questions?
Hi, Barna. I just wanted to make sure that we leave enough time for questions at the end. We are running close. At this point, we have like 6 minutes left.
Oh, okay. 6 minutes. Okay. So I will be finishing soon then. Okay. So the main idea here, like if you want to stop the error propagation from Z times, you have to somehow keep the errors local. Okay, so instead of performing, so right now I was doing the random walk in a sequential way from first block to the second block to the second block to the third block and so on. Instead of doing that, what we will be doing is to do a lot of random walks together simultaneously in each block. So you have this block 1, block 2, block 3 and so on. So you'll be performing random walk, one random walk in block 1, one random walk in block 2, one random walk in block 3 together simultaneously. And from there, you will be extracting some sequences and so on. Since I do not have time, I won't go over the exact algorithm here, but just breaking up, just making this random walk performing in a parallel way, you can actually reduce the error propagation from order of z to order of log z. And that helps to improve the approximation factor from order of, starting from order of d, we move from order of d to number of blocks, which is order of z. And then by doing parallel random walks in parallel, you can reduce the approximation factor further from order of z to order of log z. Okay, and if you see the chart here, this blue one is this order of log z approximation. And as you can see, it's very close to the optimum. So this green, light green is the optimum number of errors. And so this is supposed to be order, this is log z. So there is still a log n approximation kind of happening here. But as you can see that it's very close to the optimum. So it really performs very well in practice. And as I mentioned that this random walk techniques, it's just not has been used for Dicke distance, but it has been used for many other string problems as well, and also can help you design faster, design space efficient streaming algorithms. So before I end, I want to emphasize, like so far I had been just talking about overall time complexity and how approximation algorithms can help in overall time complexity. But in large scale data analysis, another factor that's equally important is like your data might be rapidly changing. And when your data is changing rapidly, like your algorithm needs to update the solution as the data changes. And therefore, it's not only important to have an overall good running time, but your update time of your algorithm should also needs to be very efficient. So that's the area of dynamic algorithm where the main emphasis is on update time. And that's very important when you have large data and when the data is changing over time. And in fact, approximation algorithms can be very useful in this kind of scenario. Often, if you just want to have exact algorithm, you will get stuck and you will not be able to do anything better than rerunning the entire algorithm at every step when your data changes. Whereas if you allow approximation algorithms when your data changes, like you do not have to rerun your algorithm, and you can do much better than this trivial rerunning the algorithms. And when it comes to these dynamic algorithms, there are many basic problems, even for which we still do not understand the what should be the best update time. So there are a lot of open questions here. I'll just briefly, in the next 2-3 minutes, I'll just briefly mention about one problem here, so that it just to ignite your curiosity so that you can go explore this area. There are a lot of open problems here. So let's consider the set cover problem, which you're probably all familiar with. You have a bunch of elements, you have a bunch of sets, and you want to find the minimum number of sets to cover all the elements. So that's the set cover problem. It has a lot of applications, from like in scheduling jobs, in facility location, in data summarization. Set cover problem has found like it's a lot of applications. Okay, so now for set cover, there is a very simple offline algorithm. It's an NP-hard problem, so you have to design approximation algorithms no matter what is your setting if you have to get a polynomial running time. So in the offline setting, there is a very simple algorithm which gets an F approximation. So what is F approximation? So it basically says if an element can belong to at most F sets. So we are given this collection of sets. If an element belongs to at most F sets, I will give you an F approximation. That is, if my solution requires some number of sets to cover all the elements, I will return you a solution which is within f times of the optimum solution. And there is a very simple algorithm for it, which says pick an element, look at all the f sets that contain this element, and pick all those f sets in your solution. And whatever the elements are covered, remove all those elements. Now repeat the process. Then this very basic algorithm gives you an f approximation, and its running time is order of nf, where n is the number of elements in your universe. So now in the dynamic setting, what is happening? The elements can be inserted and elements can be deleted. So you have the sets, but the elements get inserted and the elements get deleted. Okay, so you can think about like scheduling jobs where you have machines. These machines are your sets and the jobs are your elements. So jobs, when they get completed, they get deleted. New jobs can come into a system, so the elements get inserted and so on. So it's a dynamic nature. So in this kind of dynamic setting, I still want to get a solution that is good, like gives you an F approximation. So how can you do that? Do you have to run your set cover algorithm every time you have a new element coming in, a new element disappearing? And the answer was not known until 2017 or 2018. Like only very recently, like there has been progress in this area, and there is a F approximation algorithm in the dynamic setting. So it was first given by us in 2019, where we could show an F approximation algorithm in the dynamic setting with an update time, which is very close to what we could do in the offline setting. And then from there has been a lot of subsequent works as well. Since I don't have time, I am not being able to tell you the details of the algorithm. But the main idea there, again, was to use randomization. Just like you did for the random walk, you did some random, based on your outcome of your coin, you decided which steps to take. So here in this setting, again, you will do some random toss, random coin toss, and based on the outcome of your random coin toss, you will check which element shall I pick for which I will pick all these F sets covering the solution. Okay, so using this randomization essentially and approximation, so we are able to get a very efficient dynamic algorithm for set cover. And in fact, like for all the problems that I mentioned in this talk, randomization is equally a key element, just as approximation algorithm.
Hi, Barna. Sorry to interrupt, but we seem to be over time at this point.
Okay, so let me just stop here with this message that whenever you are designing approximation algorithms for large-scale data analysis, you should just keep in mind that randomization is also equally important as approximation. And so in this talk, you have learned about few techniques, like one is amnesic dynamic programming, another one is using random walk. So maybe you can take these techniques and you employ these for many other problems that you will be facing in large-scale data analysis. Okay, so thank you.
Thank you so much, Barna. Sorry, I had some Zoom interruptions in the middle. I'm not really sure we have time for live Q&A, but I was wondering whether you could answer questions on Hoover, maybe for this session and maybe in the later session offline. Is that?
I have to log into Hoover, or like what is the process? Maybe.
I can. We can send you the instructions maybe after this talk immediately offline.
Okay, that sounds good. So if there are questions there, I can definitely answer them there.
Thank you so much. I definitely have actually a bunch of questions for you.
Okay, thank you. And sorry, like I was not looking at that. It was very difficult to look at the time when you are in when you're sharing in the full screen mode. So I was not exactly sure how the timing is going on. And this online setting, it makes it so difficult to give talks as well.
It's really a very interesting topic, actually. We really appreciate it. And sorry, again, I had some Zoom problems of my own in the middle.
That's totally fine. Okay, thank you so much. Okay, so I'll look for then questions in Hoover, and if you could send me the instructions, that would be great.
Perfect. Thank you.
Thank you.